Yes.
All right. So thank you to all of you for joining to my dissertation defense today. I am Julio Diarte. I want to start first by to say thanks to my advisors, Marcus Shaffer and Jose Duarte, for their guidance and sustained support during these 4.5 years. I also want to say thanks to Loukas, Kalisperis, Benay, Gürsoy, and Professor Esther Obonyo for accepting being part of my doctoral committee and also your valuable support in this journey. I want to recognize the financial support of the Fulbright Cal Paraguay program. I want to thanks to the architecture department at the CDC and Stuckeman School, to the School of Architecture at the National University of Paraguay in Asunción, and last but not least to my wife and colleague Elena for her constant support in this work. Um, this is the dissertation's structure, and this presentation's goal is to walk you through each one of the chapters and share with you the findings and contributions. Let's start with the research problem. Uh, this dissertation explores how to take advantage of the rapid growth of urban solid waste and the potential of waste cardboard as a resource to support low-cost housing solutions in low and middle income countries. Waste cardboard is among the least valued recyclable products, and it is highly underused in these countries. The work aims to contribute with solutions to tackle the lack of decent housing in these countries where recycling and reusing rates are still low. In this dissertation, I will show you that waste corrugated cardboard has the potential as a building material to produce low-cost building parts for housing. I will also show you that the system could help self-employed waste collectors uh, to upcycle and potentially increment their revenue. Waste collectors have free access to this material but do not have the means to upcycle. Uh, let's start with chapter. First, I want to mention the research questions that guide this dissertation. Is waste cardboard a feasible material for architecture? Is addressed in chapters 2 and 3. How to make low-cost building components for housing construction with waste cardboard is addressed in chapters 3 and 4. How to enhance cardboard material properties and decrease its vulnerabilities, and what methods, tools, and technologies are needed to produce the building components with this material, and how to introduce this to waste collectors communities is addressed in chapters 4 and 5. Uh, Finally, how to formalize the proposed methods to create a building system with waste cardboard as a main component is addressed in chapters 5 and 6. Chapter 7 will revisit all these questions and discuss findings, contributions, and future work. The dissertation used different research methods for each chapter. Chapter 2, for example, was an exploratory work developing reviews and preliminary material explorations. Chapter 3 used design ethnography and case study to implement field observations and key informant interviews. Chapter 4 and 5 are more experimental work, prototyping and developing uh, building components, even at full scale. And chapter 6, it's an exploratory work where I design a building system for housing using the work that I did before, and in this case, using shape grammars. The significance of the research touches 4 different points. The first is that diverts waste for proposed waste for diverting waste cardboard from the urban waste stream to resource for construction. This has an environmental significance, especially in low and middle income countries where most of waste cardboard ends up in landfills or open dumps, and where people need alternative solutions for housing. Introduces waste cardboard as a resource for architecture. And this is important because most of the cardboard used today in architecture is brand new cardboard. And there is very little research done regarding direct reuse of material collected from the streets. Uh, the dissertation supports the work of waste collectors in low and middle income countries because, as I mentioned before, they need housing, have almost free access to the material, but do not have the means to reuse it. The dissertation provides them with tools to bridge this gap. The dissertation also bridges university and community. Here, the university serves as a resource to support collectors' works and organize co-building workshops to train them to use the system proposed here. Let's move now to chapter number 2, which is the review about cardboard in research and practice. This graphic shows the chronology of cardboard in research and practice during the last 8 decades. The emergence of Shigeru-ban buildings in the 1990s motivated the establishment of research centers in different universities. Uh, the main goal of these centers was to find new applications of brand new paper cardboard in architecture and structural engineering. The sustainability factor of paper products is still one of the main drivers of the interest in this material. Cardboard architecture chronology has two phases. The first was from 1940 to 1976, where the interest focused on structural performance, durability, thermal and moisture resistance of different composite walls. However, concerns over durability of cardboard structures under long-term loads and natural elements conceded to other materials such as aluminum, plywood, and plastics combined with foam. The same advantages and concerns were maintained in the second phase from 2000 onwards, but the interest in the sustainability of paper prevailed, and a closer collaboration between designers and engineers opened the path to significant advancements. Contemporary cardboard architecture topics are around fundamental or technical research, trying to improve the material properties of cardboards against moisture, and technology development for production of building components and their applications in architecture, always regarding brand new cardboard. The review allowed me to identify two types of structural systems in cardboard architecture: active vector and active surface structures. Most of Shigeru-ban's works fall into the category of vector structures with the use of paper tubes as main material. However, flat surface structures made with corrugated cardboard or honeycomb boards are, on the other hand, much more common. These are some of the main strategies applied to both increase load-bearing strength and decrease moisture absorption. I highlighted those that I believe are applicable in low-cost contexts, which include joints, application of joint systems, reinforcement, and stiffeners made of wood or steel, depending of the budget. Or to decrease moisture absorption, the most effective is the application of high strength cement plaster to cardboard products. This is proven to double the strength and increase moisture absorption by 80%, according to research groups at ETH and other universities in Europe and North America. To close this chapter, I want to mention that we submitted a paper about cardboard architecture, 8 decades of exploration in academic research and professional practice to the Journal of Architecture, and this is currently under review. Moving now to chapter 3, here I will talk about the field study that I did in Asunción, Paraguay. I developed an exploratory study in Asunción, Paraguay, to understand the waste cardboard collection process in a real context situation. In this work, I pay attention to the work of waste collectors, who are the potential implementers of the cardboard building system. I choose Asunción as an example of a growing urban area with very low recycling rates compared to other countries in the region and worldwide. And because there is an increasing number of waste collectors in the area. And also because most of the recyclables materials that are collected are for export and they are not really being taken advantage of in the country. I carried out field observations in the commercial area of Villamorra here in the center and interviewed different people involved in the cycle of waste cardboard in the metro area. These are some of the questions that guide my work in Asunción in December 2019 and December 2018 and August 2019. Even though people collecting urban waste are commonly portrayed as the poorest of the poor and their work as marginal, the truth is these communities play a significant role in the industry's supply chain of raw materials. Since 2000, waste pickers in Latin America transitioned from scavengers to self-employed environmental entrepreneurs and have achieved a remarkable level of organization through cooperatives and associations. Waste collectors in Asunción aren't recognized as formal workers yet. They come from poor areas of the city and equipped with three-wheelers or on foot pulling a cart. They recover aluminum, glass, paper, and cardboard. Waste cardboard, they say, must be dry and uncontaminated with food. Otherwise, they cannot sell it to the final recyclers. They are conscious of the value of what they do and the material they recover, but do not have the means, financial or technical, to learn how to upcycle materials to increase revenue or use them as a resource for building or improving their houses. Other actors playing a relevant role in the cycle of waste cardboard are, on the one hand, NGOs and startups and local paper industries. NGOs and startups focus on collection, sale, and waste management training to private companies. Both make a gigantic effort to help informal waste collectors improve their working conditions. However, none of them have the capacity to upcycle what they collect. Regarding paper factories, it is unclear how much waste cardboard they recycle. The largest paper company in Paraguay, for example, uses only 30% of recycled cardboard in the total production of brand new cardboard. According to them, waste cardboard can be recycled up to 5 times and it only serves to make more cardboard. Therefore, it is the least valued product. Paper factories, on the other hand, are equipped with high-tech tools that could easily transform brand new cardboard products into construction components. The intervention strategy seeks to take advantage of the low price of waste cardboard, its high degree of availability, and the low production level of brand new cardboard that uses recycled material. In this scenario, cardboard factories, NGOs, startups, and waste collectors can contribute to create a new value of change for the material. The research proposes to equip waste collectors in recycling reusing centers with technology provided by research developed at the university to produce building components for housing. Within this framework, the research proposed a case study that will be described in chapter 5. In this study, I work with several stakeholders, including waste collectors, NGO, startup, and university for organizing a co-building workshop. Moving now to chapter number 4, which is about methods and tools. Chapter 4 is divided in 2 parts. The first part presents craft-based and low-skill methods and tools that are intended for the direct use of waste collectors. And another part is about digital-based methods and tools to design and generate fabrication instruction of building components. The idea behind is to find simple and safe ways of reusing waste cardboard and figure out what methods can help to design and fabricate these components. The research focuses on prototypes and making as the main drivers of the investigation process. These are some of the application criteria of waste cardboard sheets used in this chapter. The criteria follows material characteristics of and cardboard packaging construction principles. These are some examples of making techniques using molds made of wood to form logs and boards. The idea was to develop tools that are easy to make, easy to use, and easy to maintain in the target context. These are some of the prototype building parts made with those tools that can be used to make panels, formwork for casting concrete panels or concrete beams. Also, in the realm of craft-based and low-tech methods and tools, the parallel winding technique, or this is a parallel winding tool that was inspired by the fabrication process of standard paper tubes used for decades in the packaging and construction industries. The process facilitates making logs or posts of variable diameter and length that could resist a load by itself or in combination with other materials. The slide shows the testing process of the tool. This was completely developed at the Stuckeman shop. Some of the benefit of these tools include that they are easy to make in the target context. They are user friendly, low maintenance. They are very good for producing a small size for using a small size of cardboard sheets. They can be automated easily and they are light and transportable. On the other hand, they need to be fabricated by professionals. They are relatively low cost depending on the materials they're used. It is not that good for making large building parts yet and requires lots of physical effort. And still the quality of the outcome is very rough and needs a further development. Let's turn now to the second part of chapter 4. The slide shows the proposed workflow of a digital-based tool developed to design tubes and molds with waste cardboard panels. Unlike low-tech tools, these digital-based tools are not intended for direct use of waste collector yet. These tools provide instructions for waste collectors to make the building components. The workflow starts with recording the size and thickness of the sheets using existing smartphone applications that are widely available in the target context. Then the digital tool receives the material documentation data, size, thickness, and compares that info with the user's design. On the top left here, we can see the different options configured by the designer. Then these are the selected options that match the existing material. And finally, the tool provides the printed instructions for cutting, scoring, and folding sheets of waste cardboard, everything done by hand. Some of the benefits of these digital tools includes increases material reuse, adapt any kind of sheets to any kind of building or almost any kind of building component shape, provide fabrication instructions for manual production, and they're adaptable to other type of flat and foldable materials. The main issue with this tool is that they require high skills for implementation. Therefore, they are not intended for direct use of waste collectors yet. The printed instructions are used to fabricate and assembly building components. This is an example of a floor panel made with OCB boards and folded tubes of waste cardboard sheets as a structural reinforcement. I also test the application of the digital tool to design and fabricate acoustic panels made with triangular profile tubes. And I perform some preliminary acoustic insulation tests at Penn State and in Asunción, comparing the prototype of acoustic panel with conventional and expensive rockwool insulation material. It turned out that waste cardboard panels have a decent acoustic insulation properties compared to rockwool. Furthermore, I use the same triangular profile tubes made with a digital tool to create ways to explore making concrete formwork. The examples here shows a modular concrete slab for a potential flooring system. This is a way in an indirect way of using waste cardboard, supporting existing building techniques. I also test the digital tool to design and make molds. These molds result very convenient to cast a screen wall for here made of reinforced concrete that could be used to protect a facade for direct sunlight or other kind of elements. Some of the lessons learned in this process of making tools and prototyping building components include that uh, molding, cold forming techniques are low cost, but require lots of handwork and improvement for improvement and work to improve the quality of the outcome. Winding tools aren't expensive and can produce cardboard logs for panel infill, but still the mechanism needs some improvements to improve quality. Digital tools facilitates dealing with waste cardboard sheets, variability of size and thickness, and create and adapt to almost any kind of shape. However, they require high skills to use. The templates generated by digital tools are uncomplicated to follow, but needs better step-by-step instructions for lay people to understand. And I'm going to show an example of this in the next chapter. So moving now to chapter number 5. So far, I show you how to make building elements with waste cardboard sheets. In this chapter, I will present 2 examples of full-scale prototype building units using all the elements shown in chapter 4. Some of the design principles used to create these prototype units are off-site prefabrication of building parts using a combination of waste cardboard and wood. I'm going to explain later why. Modular construction and incremental construction, which are principles that are appropriate for a context where things are built by parts according to the resources. The prototype unit number 1 was made with panels composed of a plywood frame and cardboard logs fabricated with the parallel winding tool. Plywood frame helps containing the logs and receive fasteners and help also connecting panels to each other. I perform a series of load-bearing strength tests on different configuration of cardboard logs. The slide shows cardboard logs with and without wood inserts. Wood inserts, in this case, increment the component's resistance. Next, I perform more tests on samples that include wood inserts and plywood frame to understand the capacity of each configuration. The example here from the right is the one that I finally applied in the prototype unit number 2. The full-scale prototype unit number 2 helped me to test the process and identify some issues on the system. The slide here shows different observations related to execution and quality. The work was developed at the school shop and building yard. Here, for example, on the top left, there is an observation on the inconsistencies of the size of the logs and the gaps in between them that is important to correct, or observations regarding connections of the panel to the floor platform and how to improve the strength of those connections. The full scale, yes, sorry. Let's move now to the second prototype unit. The goal of this prototype unit was to test the use of cardboard tubes instead of cardboard logs, and also layer sheets with a plywood frame to make a floor, a ceiling, and a wall panel system. In addition to this, I wanted to test fabricating this with waste collectors in some kind of a real context situation. Therefore, I organized a workshop in Asunción, Paraguay for doing this. But before going to Paraguay, I was able to perform some load-bearing strength tests in order to understand the component's capacity to vertical loads and use it as a structural element. I test different samples with triangular profile tubes, and this is the sample that I use for the prototype. I did additional tests, including the plywood frame, seeking to simulate the situation of wall panel for prototype unit number 2. And thinking about the workshop, these are some of the different questions that I use as a guideline to organize the co-building workshop. Some questions are related to material collection, building parts fabrication, and building assembly. The workshop used 1.2 tons of waste cardboard sheets provided by collectors and an NGO. This is the place where I did the workshop. The workshop was held at the Center for Research, Innovation, and Development at the Architecture School in Paraguay in August 2019 and last for 5 days. I worked with 4 waste collectors. Some of them had little experience in self-construction of their own houses. This is very common in Paraguay. People are used to participate in the construction of their houses, especially in low-income families. But none of them ever use the cardboard they collect to build something. Waste collectors were involved in the fabrication of cardboard panels, assembly wall of panels, and assembly of the unit. They did not participate in the fabrication of wood frames due to safety concerns. These are some images illustrating the process of the workshop that applies the workflow for fabricating the waste cardboard components. On the left, these are the preliminary work, selecting, trimming. This is the work where they use the templates provided by the digital tools to score, cut, fold these cardboard components. Pictures of the process of the application of fungal and insect attack protection based on previous research developed by other research centers. And here on the right, images of the full assembly of the prototype unit. A few lessons learned out of these experiences include that cardboard occupied 8% of the materials budget in prototype unit number 2, 60% of the construction volume, and only 15% of the construction's weight. To confirm that the low cost of the material and the lightweight of the material as well. On the other hand, plywood took 74% of the materials budget, and this is very high. However, redesigning the plywood frames could reduce 30% of its cost. The prototype unit cost is 20% more expensive compared to the cost of an equivalent construction made with traditional building materials in Paraguay. However, replacing wood with other materials and mass production could help reducing the system's cost. As conclude, after interviewing participants, learning the process of making panels with waste cardboard sheets was very straightforward for them. But assembling wood frames was not and required much more training time. Parts of chapter 4 and 5 were published as a book chapter of the CAD Futures Conference 2019, and also in other proceedings of conferences at Georgia Tech, conferences on computational design as ECADI SIGRADI, or conferences about materials or waste or reuse of waste materials. Okay, so the goal of chapter 6 is to close the loop of the research by applying the previous results to devise a full modular housing system that could be used in the target context. And in this case, I'm using shape grammars to combine those tools and create a design system. In this exploration, shape grammars act as a tool to generate housing floor plans based on a local typology from Asunción. The slide shows an example of a sausage house typology. This typology is quite common there and allows building by stages. This method is ideal for low-income households who build their houses according to available resources. And the typology, although, allows to adapt the floor plan to plots of different dimensions and respond well to local climate. These are some of the reasons that I use this as an excuse to experiment the system. Shape grammars is a rule-based algorithmic system used to create and understand designs by computing shapes and defining design languages. The grammar structure of the housing system has two parts. The first deals with the design of the layout of the house, and the second deals with the fabrication of the panels made of waste cardboard and wood frame. The shape grammar structure include processes shown in chapters 4 and 5. This slide shows part of the rules created to design the layout of the house. Starts with defining the plot and placing the first room, and follows with the incremental addition of rooms until completing the programmatic needs of the house. The grammar follows local social housing standards as a guideline to design the layout. On the left is an example of rules derivation, and on the right is a visualization of a floor plan generation. After designing the layout of the house, the grammar facilitates to generate the templates to fabricate wall panels, including waste cardboard components and wood frame. Then the wood frames are filled with panels made of waste cardboard tubes, and these are the rules indicating how to place those tubes to create these panels. Finally, the grammar offers a set of rules to guide the fabrication process of waste cardboard components. The fabrication process in this case is completely made by hand. And this is an example of on the right, where the grammar combines the templates generated by the digital tool presented in chapter 4 and the derivation of the rules that I show you here on the left to create these cardboard panels, exactly like this one that you are seeing here. The work in this chapter was published at the proceedings of the CALJA 2020 conference that was held last August. So now, chapter 7 will discuss finding, contributions, and future work. And for doing that, I want to bring those questions that I shared with you at the beginning. Is waste cardboard a feasible material for architecture? I believe yes, we can reuse waste cardboard directly or indirectly to make buildings, because there is an increasing interest on reusing more recyclable materials. It is low cost and available. It has low recycling rates in low middle income countries, and the proposed reuse system for housing is applicable in the target context, as shown in the experience of the workshop. The research offers design principles and fabrication methods for direct or indirect use of cardboard as a building resource. And the research proposed a strategy to converge different stakeholders to support waste collectors in producing low-cost building parts for housing. How to make low-cost building components with waste cardboard? I think there are two ways of doing this. One is to use waste cardboard to create building elements for direct use in construction combined with other materials. The example is the example of the wall, floor, and ceiling panels, and acoustic and thermal panels. Uh, or you can use waste cardboard to support existing building methods. And this is the example of indirect use as concrete formwork. The research shows a path for implementing cardboard reuse in both ways, direct or indirect, by establishing fabrication criteria of building parts, resource need, and examples of prototype parts. About how to enhance cardboard properties and decrease the vulnerabilities of the material, I can say that it is important to maximize its use for non-structural applications, partition walls, ceilings, acoustic panels, or combine it with wood or metal, depending on the budget, if used for structural applications. You can also minimize its contact with moisture and fire by impregnating waste cardboard with cement plaster and or adding other layers of water-resistant materials such as plywood, cement boards, or galvanized siding panel. The research develops low-tech strategies to reinforce waste cardboard components and protect from vulnerabilities. Regarding methods, tools, and technology and how to translate these to waste collectors, uh, the findings include that low-tech methods such as molding, cold forming, winding, cutting, etc., are relatively easy to apply by hand to reuse waste cardboard sheets. The digital tools help dealing with variability of sheets to design building components of different shapes. Waste collectors can learn and apply these fabrication instructions for making the building parts. Co-building workshops are a valid way to translate the system and help validating the use of the material. The research develops tools to create templates of building components and their application for the construction of full-scale modular architectures. And it offers a model of co-building workshops to implement the building system. About formalizing the proposed methods, the findings include that waste cardboard components adapt easily to panelized building system for housing. Shake grammars can help to structure all the procedures for designing a housing system with waste cardboard. In this case, the contribution is a shake grammar that encodes all the procedures for customizing housing layouts using this material and a system for assembling them. The system includes the procedures, a system for assembling them into housing solutions, and a grammar that includes the first two, and that can eventually be used to generate a computer program that implements the grammar. Then it can be used to generate customized housing solutions and generate instructions for making and assembling the parts. Regarding future work, I intend to continue working on practical applications of cardboard systems for modular constructions and social housing. In this regard, I want to mention that the prototype unit number 2 that was built during the workshop in Paraguay will be used at the Center for Research in Paraguay as part of their research facilities. The fabrication of detached modules for different uses, in this case, is a future line of research that I want to pursue. I am interested in social housing in low and middle income countries, and I have been in contact with an NGO from Paraguay, Fábrica Social de Viviendas, for a collaboration to implement waste cardboard as acoustic panels in their houses. And finally, I want to continue researching the indirect use of waste cardboard to make formwork for casting concrete. In this regard, a proposal that Marcus and I put together for the Seoul Biennale 2021 was shortlisted, and I hope to present, we will present the research next year at the Biennale. To conclude, I have these 5 main points. First, I believe it is possible to reuse waste cardboard into building parts, but it is very important to continue investigating ways of improving the quality of the parts and durability. And for this, the collaboration with structural engineers is very important. It is possible to develop a comprehensive housing system from those parts, but this required extensive collaboration with stakeholders to validate the use of these materials for housing. Lay people can follow and apply procedures developed in this research to make building parts out of waste cardboard, but more instruction is needed to enhance their building capabilities and produce, for example, wood frames. Waste cardboard can support the building capacity of collectors in low and middle income countries in two ways: direct use of low tech and craft based tools, and indirect use of digital based tools. For doing this, collaboration between university and community is critical, and this can help mediating between low and high technologies for practical applications of the building system and to adapt the system to different contexts. And this is my last slide. So thank you so much for your attention. And now the floor is open for questions.
Thank you, Julio. Thank you very much.